Welcome back to POE. Today we're going to be talking about Introduction to Series Circuits. Specifically, a series circuit is a circuit that only contains one path for current to flow. And if we look through here at this series circuit, the electricity would obviously be going from the negatives. It's a flow of electrons, so we're going to have electricity or electrons that are flowing in this direction. And if you see, never does the electrons ever have a choice. It has to go through this light. Then it has to go through this light. There's no choice, no different paths for it to take. Well, let's give you some common characteristics here of series circuits. Characteristics of a series circuit. The current flowing through every series component is equal. And what that means is the current, the flow of electrons, the I, has to be the same, because you notice never does it have a chance to split. If you think about a river flowing, if we had a river flowing, at some point there might be the big tributary, and then off you have all these maybe little branches, little creeks and everything that come off. Well, what happens then is all these little creeks get less current than what you started out with. Along with this as well then, the voltage, alright, the voltage is a sum of all the voltage. And what that means, for example, is we've got 12 volts down here. Let's just forget about all these numbers and throw some numbers here. Let's say this one here was getting 4 volts. This one here was getting 5 volts. Well, what that tells us then is 4 plus 5 is 9. There's a total of 12 volts. This one has to be using 3 volts. And again, I could care less about this information right here, right now. What that means then is we talk about the voltage drop, or the potential difference. That means there was 12 volts here. This uses up 4 of those volts, and there's only 8 volts left. So there was 8 volts here. It uses 5 of them. There's only 3 volts left once it comes through. Because remember, voltage is like pressure. Think of each of these being a sprinkler. They're going to use up some of that pressure. When we get over here, there's 3 volts. It has a drop in 3 volts, so there's 0 volts once we get over here. All of this is called Kirchhoff's law, meaning it's all going to balance out for the most part. I guess is an easy way of remembering that. Series circuits. Well, how do we find the individual components? Meaning, what's the voltage going through the first one? What's the voltage going through the second and the third? What's the current going through the first? What's the current of the second? What's the resistance? What's the total voltage? Well, the steps here. The first step you're going to want to always do is find the total resistance. All right, the resistance total, and you're going to see that quite often is just RT. It might be a little subscript T. It might be a capital T. Sometimes they'll have it like this. Sometimes they'll just have it like this. Sometimes you'll see it like this. But what that means is the total resistance. If you add up all of them together, what does it add up to? The same thing then for the current. The second thing you're going to want to do is find the current. The third step along the way is use your characteristics. These characteristics we just told you right here about this. Other things about the characteristics here is the current is always the same. All resistors get the same current. That's going to be your when you're dealing with series circuits, that's the characteristics we're talking about. And then when in doubt, use your equation, V equals IR. That's the golden equation, you could say, for this. Well, series circuits. What we're going to do here is we want to go through and find each of these individual components. The first step was to find RT, find that total resistance. What I've done here is I've taken all the resistors, 220, 470, and 1.2 kilo ohms is 1,200 ohms if you convert it using the metric system. If you add those all up, we get 1890. What I'm going to do, I probably should have done to start off with, is fill in the information that they tell us. The total voltage is 12 volts. They tell us then that R1 is 220, R2 is 470, and R3 is 1200. I want you to notice that I'm making this table, and you're going to hear me refer to make the table. Make the table. Make use of the table. Well, the second step here now is to find IT. Find your total current. Well, how do I find IT? I go back and use my equation, V equals I times R. And I'm going to simply say V equals I times R. Voltage here is 12. The current is what I want to know. The resistance is 1890. And the current here then turns out to be 0.006 amps. Now we wouldn't typically use that. We're probably going to convert it to milliamps, which would allow us to move the decimal over, and we'd probably say this is 6 milliamps. So this becomes 6 milliamps. Well, our third step, it says use the characteristics. What do we know about a series circuit? We know that all of them get the same current. So that means if the total is 6 milliamps, then all of them get 6 milliamps. Now this works for series circuits. Our last step is use V equals I times R. So to go about doing that, then I'm just simply going to multiply these two numbers together each case. I did this real quickly, and it all comes down to some rounding that we go along here with this as well. But roughly 220 times 0.006 gives us 1.7. Multiply the R2 times I, and it gives us the voltage. R3 times I3 gives us V3. So that's the steps I went through there. Okay, real quickly, I'm going to talk a little bit about the symbols. A diode, here's an example of a diode. A diode is not much different than a light bulb. It's still going to have current that goes in and a current that goes out. Resistors, we're going to talk a little bit here about resistors. Here's several different examples of them. Notice these are carbon fill 4 bands. This is carbon film 5 bands. We have surface mount resistors. We have potentiometers, meaning it can change its variable resistance. Some of you have at your house, you have lights. You can turn the knob one way or the other and it dims the lights or turns them on. Here's examples of resistors. Notice most of them are about the size of a dime, if not smaller. Determining a resistor's value. Well, this comes down to color code. You can either measure a value or we can look at the color code. We're going to real quickly try to teach you to look at the color code. It's been a while, but we'll look at it. Basically, what you're going to do is you're going to look at the 4 bands on here. And the first band, all right, tells you, and you have a color here. And that's what this is going to tell you is the value. And for example, the first one is an orange. They have a white. A green one is the multiplier. And the last one tells you the tolerance. The lower the tolerance, the more expensive, meaning 5%. It's only going to vary. A resistor could vary up to 5%. This one, a silver one, could vary up to 10%. This one could vary up to 20%. That would be the cheapest, 5%. The gold bands are going to be the most expensive. Well, let's take a look then what this means. In this case, we have a brown one, a black one, and a red one here, and a tolerance of 5%. Well, to go about finding that, then, we find out that it's 10. The first one is 10, or 1, and then 0, which gives us 10, times 100 ohms, which means it's going to be 1,000 ohms, and it's going to have a tolerance of plus or minus 5%, which means it's 1 kilo ohm plus or minus 5%. Yes, if I was you, I'd be getting this information right here copied down, whether you want to or not. Here's another one. All right, orange, white, green. In this example, the orange is a 3. The white is a 9, so it's 39 times green times 100,000. That K stands for 100,000. And they're going to tell us it's a yellow, so it's at 5% again, plus or minus 5%. What we find out then is this turns out to be 3,900,000 ohms, or 3,900 kilo ohms, plus or minus 5%. Well, hey, that's it for tonight. I'll see you on the flip side.